Okay. This is the general drag, right? But can I also calculate the V that goes with it? And the answer is absolutely. We go back to our original equation, which was A. Can I rewrite this equation again? Sigma F equals mg minus d. Imagine there is no acceleration. I'm at terminal velocity. This goes to 0. May I write this as d equals mg? May I plug in d here? 6 pi r eta v. Can I write rho vg? Can I cancel those two v's? Why? Be careful. You cannot cancel them. One is a volume and one is a speed. Even though my handwriting is terrible, you're not allowed to make fun yet. Good? So then may I write this V as 6 pi r eta. And if I talk about a sphere, what's the volume of a sphere? May I plug that into here? What will I get? Rho 4/3 pi r cubed g divided by 6 pi r squared eta, or 2 over 9 pi r eta g. So I'm trying to put all the constants together. Rho and r. Wait, why did I get an r squared there? This should be just an r. I messed up. There should not be an r squared here. There should be an r here. So I'm going to try to put all the constants together. Correct me when I mess up. So this will be rho, pi will go away, 2 over 9, one of the r's goes away, eta g r squared. Am I missing something? So that means, honestly, that's the difference between going in a pipe and going in free space. Yes.
Won't eta also change though? A lot of times, you know, different pressures. Different
True, but not, hopefully not in the same fluid.
Oh,
So-
I see what you mean.
So yes, they will change when you change fluids, but it shouldn't change when you have the laminar flow in a fluid. But yes, eta will change. We do still want to keep a steady state. We do not want tubular motion because that's going to be a mess.
I was with, you said being with a paint drop as it was falling, would it get other datas? I guess.
True. True, but we're almost going to assume that it is kind of constant. And we're not making, again, also recognize I'm talking terminal velocities.
Yeah.
I'm saying, remember I started talking about terminal velocities and when that happens?
Yeah. So,
Yes. Technically, yes, it'll change, but not to the point where it will affect it that much. Yes.
Ignore like temperature gradients.
Oh yeah, absolutely. One of the things you have to remember, yes, those things exist, but do you remember when we were doing the pressure changes as it goes up?
Right.
And we ignored the fact that yes, we understand gravity will change. We also understand temperature will change, but in the question itself, I'm going to ignore those and then do the problem. But of course, they all will change and they all have an impact. Also, remember when we were doing the rockets flying up and we said, yeah, there will be drag, but the effect of it is so small that, and it lasts for such a small interval of time, we are not going to do that calculation here. However, if you do become a rocket scientist, that is the time where you have to put all those things back in. Understand, this is a very generalized way of looking at stuff. When you actually do get into the nitty-gritty of it, there are entire courses that are taught on this one thing. Fluid dynamics, fluid flow. Like When you go into your engineering schools, you will be taught entire courses on this stuff. I am just trying to give you 1 day's worth of math. I mean, we could do more, but that just means we're spend the entire semester on this, which you will eventually, but that is not our job right now. So yes, I understand I'm ignoring a lot of things, but that is by design, because I want you to be introduced to everything in case you want to go into a particular field, right? Also, can you guys see how scary these equations look? But do you see me developing them from very simple ideas? That's the thing I want you to learn from this class. How do I make very scary looking things seem not that scary? Because I know how to develop them. Do you think I remember this equation? No. But can you figure out how to develop them is the task. And that should be simple. We should all be able to do that.